Now this is the book's picture for the very same demonstration, that each of these dots on the pink curve represents one of the numbers in the sequence. And this sequence has a limit, which is represented by the horizontal line y equals L. How did we figure this out? Well, perhaps my sequence A sub n actually has one of these formulas. And again, we have taken that formula and we're treating it as a function of real numbers, x instead. And this function, the pink curve, has a horizontal asymptote. So the limit of f of x as x goes to infinity is L. So notice that the function actually crosses that horizontal line, it deviates away, and then it comes back and joins it up later in the limit. So because we are using the same general ideas of limits, then we can use the same rules that limits followed in Calculus 1. So if we have two different sequences which are convergent, which just means that their limits exist, then all of the same rules that we would expect from Calculus 1 still work. The limit of the sum of two sequences is the sum of the limit of the sequences taken separately. The limit of the difference of two sequences is equal to the limit of the first sequence minus the limit of the second. The limit of some constant c times the elements in a sequence is equal to c times the limit of that sequence. The limit of a constant by itself is just a constant because it's not changing. The limit of a product is equal to the product of a limit, as long as both of those limits exist again. The limit of a quotient is equal to the quotient of two different limits, so long as that denominator is not going to 0. And finally, the limit of a sequence, where I've taken this to a power, is going to be equal to the limit of the sequence by itself, and then whatever that limiting value is, we raise it to a power. And this rule actually has two caveats, just like it did in Calculus 1. The power has to be positive, and my terms here also have to be positive, just to make sure we don't run into any trouble with, square roots of negative numbers and that kind of business. Now, in Calc 1, we had the squeeze theorem that tells me if one function is always sandwiched between two others, and the two functions on the outside have the same limit, then the function in the middle is squeezed and it must have the same limit as the two functions that are bounding it. So the very same thing happens for sequences too. And again, all of this goes through, again, because of this kind of picture. Everything that we're doing for limits of sequences is pretty much the same idea of limits of functions, just the domain is slightly different. But the same ideas that we have previously built up in calculus still work here. So we get the squeeze theorem for sequences like this. Now, the squeeze theorem gives us a handy tool for telling when a sequence goes to 0, right? When is the limit of this sequence equal to 0? Well, if the limit of the absolute value of that sequence is equal to 0, then my limit must be 0. And more generally, just like we saw in Calc 1 that continuous functions play very nicely with limits, the same thing applies for limits of sequences too. So if you have a sequence a sub n, and the limit of this sequence is equal to L, the limit of f of an, so long as the function f is a continuous function, will just be f applied to the limiting value, L. So what are these things saying in terms of my picture? Well, maybe my sequence isn't actually 1 on 2 to the power n. Maybe my sequence is minus 1 to the power n on 2 to the n. So now my blue dots, sometimes they are below the x-axis, sometimes they are above the x-axis. Well, to use the squeeze theorem here, I just need to say that there's some sequence that's always larger. So I'll use positive 1 to the power, positive 1 on 2 to the x. And I'll need some sequence or some function which is always less than or equal to. So I'll use minus 1 on 2 to the power x. And now since both of these curves have the very same limit as x goes to infinity, they're both going to 0, then the limit of this blue sequence must also be 0.